Welcome back to Basic Electronics. In this lecture, we will look at the input and output resistances of the non-inverting amplifier. We will also look at a special case of the non-inverting amplifier, that is the op-amp buffer. So let us begin. Let us look at the non-inverting amplifier once again. Here is the circuit. The input voltage goes to the non-inverting input of the op-amp. From the inverting input of the op-amp, we have R1 going to ground and R2 going to the output node of the op-amp. And the load resistance is not shown here because that's not really a part of the amplifier circuit. Let us redraw this non-inverting amplifier circuit as shown here. It looks different, but it's the same circuit, same connections. So Vi connected to the non-inverting input once again. From the inverting input of the op-amp, we have R1 going to ground and R2 going to the output node of the op-amp. Here is another way of drawing the circuit. Again, Vi connected to the non-inverting input, and from the inverting input, we have R1 going to ground, R2 going to the output node. Yet another way, Vi going to the non-inverting input again, and from the inverting input we have R1 going to ground and R2 connected between the inverting input of the op-amp and the output node of the op-amp. So there are these seemingly different ways of drawing the same circuit, and we might come across these in some real examples. So we should be familiar with these different ways of drawing the same circuit. We now consider a special case of the non-inverting amplifier with R1 very large and R2 very small. If R1 is very large, say infinite, we can remove this resistor. If R2 is very small, say 0 ohms, this becomes a short circuit, and we get the circuit shown here on the right side. Now let us see what VO is in terms of Vi. For the non-inverting amplifier, as we have already seen, VO divided by Vi is 1 plus R2 by R1. R2 is 0, R1 is very large, so this quantity simply becomes 1. So that means VO is equal to Vi because the gain is 1. And we can also observe this directly from this circuit. Since the op-amp is operating in the linear region, V minus and V plus are nearly equal. So V minus is also equal to Vi, and since that is connected directly to the output, VO is also equal to Vi. And this circuit, the one on the right, is known as unity gain amplifier because the gain is 1, or voltage follower because the output voltage simply follows the input voltage, or buffer. And why it is known as buffer, we should see very soon. The question is, what has been achieved by doing this? We have got an output voltage which is just equal to the input voltage, no gain. So is this circuit useful at all? It turns out that it is very useful, and we will see how it can be used. Before we look at the buffer circuit, let us discuss something called loading effects. Here is a signal source which is represented by a voltage source in series with a resistance Rs, and we want to amplify this signal voltage and apply the amplified voltage across the load resistor RL. And we do that using this amplifier. The equivalent circuit of the amplifier is represented by the input resistance Ri, the voltage gain AV, and the output resistance RO. So what we would really like to have is VO to be equal to AV times Vs. Let's say we have Vs equal to 1 millivolt and the gain of this amplifier is 100. Then we would like to have an output voltage of 100 times 1 or 100 millivolts. Now in reality the actual output voltage is slightly different, and let us see how. This VO is not quite AV times VI because there is a voltage division here. So it is AV times VI multiplied by RL divided by RL plus RO. That is this expression here. Also this VI, the voltage across the amplifier input terminals, is not quite Vs, and again there is a voltage division here. So it is Vs times Ri divided by Rs plus Ri. So the net VO is given by this expression here. This is less than 1, this is also less than 1. So this whole gain is not AV but something less than AV, and that is not desirable. What we would really like is VO equal to AV times Vs. This reduction in gain from AV to this number is referred to as the loading effects. It represents the loading of the amplifier by the load resistor RL and also loading of the voltage source by the amplifier, that is this input resistance of the amplifier. Is there a way to minimize or eliminate these loading effects? Let us see. Suppose we make Ri very large, then Ri plus Rs is about Ri and this factor becomes equal to 1. Similarly, if we make Ro very small, then Ro plus RL is nearly equal to RL. This factor also becomes 1. And then we have the gain equal to AV times 1 times 1, and that is just AV as we would like. And the buffer circuit that we have seen in the last slide, or also called the voltage follower, provides exactly these features, and that is why it is very useful. We now want to look at the op-amp buffer, find its input resistance and output resistance. To begin with, let us look at the non-inverting amplifier, because the buffer is a special case of this circuit with R1 equal to infinity and R2 equal to 0, as we have seen before. Now for this circuit, let's replace the op-amp with its equivalent circuit consisting of the input resistance, gain element and output resistance. And to obtain the input resistance, what we do is apply a voltage source Vs here, find this current Is, and then the input resistance of the non-inverting amplifier, as seen from here, will be Vs divided by Is. To get Vs over Is, there may be different ways of doing this. What we will do is to treat Va, the node voltage at A with respect to ground, Vb, Vi, the voltage that appears across the input terminals of the op-amp, that one, and Is. So we will treat these four quantities, Va, Vb, Vi and Is, as our unknowns. We will treat this Vs as a known number, and then we will obtain equations which will enable us to solve for Is in terms of Vs. Let us begin with KCL at node B. What do we have at node B? We have this current plus this current plus this current, and these three currents must add up to 0. This one is VB divided by RL. This one is VB minus the node voltage here, which is AV times VI with respect to ground. So VB minus AV times VI divided by RO, and this current is VB minus VA divided by R2. So these three must add up to 0. That gives us KCL at node B. What about the source current? The source current is the same as the current through this RI, and that is the sum of two currents, this current here and that current. This current is VA divided by R1, and that one is VA minus VB divided by R2. So that is what this equation says. IS is equal to VA by R1 plus VA minus VB by R2. In addition to these two equations, we have two more conditions. One is VI equal to IS times RI. This VI is IS times RI, and VA is VS minus VI. This node voltage is equal to Vs minus this voltage drop. So it is Vs minus Vi. So we have four equations, 1, 2, 3, 4, and we have four unknowns. What are the unknowns? VA, VB, IS and VI. And remember, we are treating Vs as a known quantity. So we have four equations and four unknowns. We can solve these and obtain Is. Once we obtain Is, we can find the input resistance as seen from there as Vs over Is, and that turns out to be this expression here. It is a bit messy, and you are of course encouraged to do all the algebra and arrive at this result. But let us look at least the dimensions of this Rin, whether it is indeed ohms or not. What about the numerator? Dimensionless, dimensionless, dimensionless. Ri, and this whole quantity has units of 1 over ohms, so ohms by ohms. So this entire numerator is dimensionless. What about the denominator? 1 over ohms. This is dimensionless, and this also is 1 over ohms. Ohms by ohm squared, so 1 over ohms. So the denominator has dimensions of 1 over ohms, and therefore this entire expression is in ohms. The stop sign has come, and it is telling you that you have to work out this relationship and then proceed further. It's a bit of algebra, maybe a page or so, but it is definitely worth doing. Let us try to simplify this expression for the input resistance. We know that Ro is much smaller than all of these resistances. R1, R2, RL would be in the kilo ohms range, whereas Ri would be in the mega ohms range, and Ro is much smaller than all of those. It would be something like 50 ohms. So therefore these ratios, Ro by R1 or Ro by R2, etc., would be much smaller than 1, and we can ignore those. So we can ignore all of these terms containing Ro in this expression and get a simplified expression given here. Now in this expression, this one is much smaller than this second term. This represents R1 parallel R2. So the first term here is Ri divided by R1 parallel R2, definitely would be much larger than 1. So therefore we can ignore this one and then simplify this expression to this quantity, and then after a bit of algebra we get our final result. This R1 divided by R1 plus R2 is smaller than 1. Let's say 1 by 10, 1 by 20, 1 by 50, something of that order. Now AV times Ri is a very huge resistance. AV is 10 raised to 5 for the 741, Ri is 2 mega ohms. So altogether this input resistance is very large, and therefore for all practical purposes we see an open circuit from this terminal. And this very large input resistance is definitely a big advantage of using the non-inverting configuration. Let us get back to the op-amp buffer circuit, and we are interested in finding its input resistance as seen from here. First, we replace the op-amp with its equivalent circuit shown here, consisting of the input resistance, the gain element, and the output resistance. We apply a voltage source Vs and find this current, and then the ratio of Vs and Is gives us the input resistance as seen from the non-inverting terminal of the buffer. As before, we will assume that Ro is very small with respect to other resistances, and we will treat it as 0. First, let us look at Vs, this voltage. So what we will do is we will start with 0, we'll go like that. We come across a rise of AV times Vi, then go like that. Ro is 0, so there is no voltage drop there, and then go like this. So that is a voltage rise of Vi. So altogether we come across a voltage rise of AV times Vi plus Vi. So that is AV times Vi plus Vi, or Vi times 1 plus AV. That is Vs. What about Is? This voltage drop is Vi, and that is simply Is times Ri. So that gives us Is, Vi divided by Ri. And now all we need to do is to take the ratio Vs divided by Is. So Rin, as seen from here, is then Vs divided by Is, which is Ri times AV plus 1. And this of course is a very large input resistance. Ri is a few megohms and AV is 10 raised to 5, so it is really very huge. So that means looking from here we see a very large input resistance for the op-amp buffer. Let us now look at the output resistance of the op-amp buffer, and let us start with the non-inverting amplifier, because buffer is a special case of this circuit. What do we mean by the output resistance? What we mean is the resistance as seen by the load resistor here. And first what we do is replace this op-amp with its equivalent circuit as shown over here. The rest of the connections of course are the same. We have R1 going to ground from the inverting terminal in both cases, and R2 between the inverting terminal and the output terminal. Here is our RL, and Rout is defined as the resistance as seen from RL, like that. And how can we find Rout? We deactivate the input source first, that means connect this node to ground. Replace RL with a test source V prime. So we remove RL and put a voltage source V prime over there. Find the current I prime through V prime, that current, and then Rout is given by V prime divided by I prime. So let us do that. Okay, so this is what we do. We deactivate the input voltage, that means connect this node to ground. We replace RL with a voltage source as shown over here, and now we find the ratio V prime divided by I prime, and that will give us the output resistance. Alright, to begin with, let us mark the node voltages. This node is at V prime with respect to ground. This node is at AV times Vi with respect to ground again, and this node is at minus Vi with respect to ground. Now this voltage minus Vi can be related to V prime when we realize that this R1 and Ri are actually in parallel. So from this node we have two resistances going to ground, R1 and Ri. So they are actually in parallel. So we have a single resistance R1 parallel Ri going to ground from this node. And once we figure that out, we can obtain this node voltage. So minus Vi would be this R1 parallel Ri divided by R2 plus R1 parallel Ri times V prime, and that is simply voltage division. So this is what we get for Vi in terms of V prime. And notice that Ri is a large resistance, is the input resistance of the op amp, and therefore Ri parallel R1 is nearly equal to R1. So what we have over here is essentially R1 by R1 plus R2, and that fraction has been defined as K over here. As an example, let us say R2 is 9K and R1 is 1K, then this fraction would be 1K divided by 10K or 1 by 10. Let us now look at this current I prime. What is I prime? It is I1 plus I2. And let us now get I1 and I2 individually. What is I1? V prime minus AV times VI divided by RO, the first term. What is I2? V prime minus VI divided by R2, the second term here. And this VI we can replace with minus KV prime. So that gives us I prime equal to 1 over RO times V prime plus KAV V prime. This term here comes from here, plus 1 over R2 times V prime plus VI, and VI is minus KV prime. So 1 over R2 times V prime minus KV prime. So that is our I prime. So we now have I prime in terms of V prime. All of these are in terms of V prime. And we can now obtain I prime divided by V prime. What we want is V prime divided by I prime, the output resistance. So let us do that. So I prime by V prime is 1 over RO, 1 plus K times AV, the first term here, plus 1 over R2, 1 minus K, the second term here. So this is like the conductance, and it's a sum of two conductances. So the resistance, which is the reciprocal of this quantity, which is the output resistance we are looking for, is basically two resistors in parallel. One of them is RO divided by 1 plus KAV. The other one is R2 divided by 1 minus K. So that is what we get for the output resistance as seen from RL. Now of these two, this resistance is clearly very small because we have RO here, and RO of an op amp is a small resistance, and therefore a small resistance in parallel with a larger resistance is essentially that smaller resistance itself. So then we have R out approximately equal to RO divided by 1 plus K times AV. Now AV is a large number, 100,000 for the 741 op amp, so therefore this quantity is actually a very small resistance. Let us now take the special case of the op amp buffer. How do we obtain the buffer from the non-inverting amplifier? We make R1 infinite and R2 equal to 0. Now this K, which is this fraction here, will become 1 when R2 is 0, and therefore this expression for R out will now become RO divided by 1 plus 1 times AV, or RO divided by 1 plus AV. AV of course is the voltage gain of the op amp, the open loop gain, which is a large number, 100,000. RO is already very small, something like 50 ohms for the 741, 50 or 75. So this quantity is really tiny. So for all practical purposes, we can treat R out as a 0 ohm resistance. So the op-amp buffer not only provides a very high input resistance, it also provides a very low output resistance. So let us keep these desirable features of the op-amp buffer in mind. To summarize, we have found expressions for Rin, the input resistance, and Ro, the output resistance of the non-inverting amplifier. We found that Rin is very large and Ro is very small, and that makes this circuit very useful in certain applications. We also looked at the op-amp buffer, which is a special case of the non-inverting amplifier. In the next class, we will look at how a buffer can be used to avoid loading effects. Until then, goodbye.